This video supplements and accompanies the white paper titled A More Complete Understanding of Power and Information Flow in Circuits and the Origin of Electromagnetic Interference. The motivation for the paper is the challenge I found with the understanding of many practicing engineers of the nature of electrical information and power flow in circuits, whether relating to electric power transmission lines, television signals in a coaxial cable, or digital signals on a printed circuit board. The example shown here will be for the latter, digital signals on a printed circuit board. The concepts, however, hold for any and all applications and circumstances. Introductory circuit theory courses introduce tools of circuit analysis via the concepts of voltages and currents. Tools, such as Kirchhoff's laws, are introduced, and these tell us how to manipulate these parameters and techniques known as nodal and mesh analysis. Nodal and mesh techniques tell us how to resolve or calculate the voltages and currents at any desired point in a circuit. The key is that at this early stage, the connection between voltages and currents and electric and magnetic fields is often not made. In fact, what is often taught at this early stage is something I call the hydraulic analogy. The more nuanced understanding is left for later courses that are rapidly becoming electives and may never appear in an undergraduate curriculum. The hydraulic analogy. Current is defined as the number of charge carriers that pass a point in a circuit in a given unit of time. Voltage is defined as the energy needed to move a unit of charge from one location in the circuit to another. To provide a mechanical reference to which most students will be able to relate, voltage is often compared to pressure. That is, voltage is often presented as the electrical analog of pressure in water pipes. Pressure difference being the motive force that moves water from one location to another. In this case, voltage is the motive force or pressure moving point-like electric charges from one point in the circuit to another. The image that is formed is that of tiny electric points being pushed through the wires in a circuit like beads in a straw. This hydraulic analogy is useful for the analysis of low-frequency circuit applications. However, information and power flow, as we shall see in the next few slides, is not solely the movement of tiny electric charges in wires. Rather, it is always and everywhere an electromagnetic field disturbance moving through some dielectric or insulating material. Most engineers will make this shift from the simpler but incomplete hydraulic analogy to the more nuanced view of electromagnetic field disturbances when they encounter RF, microwave, or optical frequency applications. What is shown here is an animation involving traces on a printed circuit board. Before we discuss the animation in detail, let's review the system. In Figure 5a on the lower left, we find what is known as a microstrip. These are nothing more than traces on a printed circuit board. The traces are thin strips of copper that are applied to the top of the printed circuit board. They are flat wires that manage the digital signals that are impressed on them. On the bottom of the circuit board is another layer of copper known as the ground plane. Sandwiched between the copper traces and the copper ground plane is an insulating or dielectric material. FR4 is a commonly used material. Together, the top traces, the bottom ground plane, and the dielectric substrate form a transmission line. These are the minimum elements needed to transmit information, for example, digital signals, as well as power. That is, two conductors and a dielectric medium between them. Now, back to the animation at the top of the page. What is presented here is a series of finite element analysis-based computer simulations that provide direct visual evidence of the nature of how signals, both information and power, are transmitted in circuits. These simulations are not artistic interpretations. Rather, they are the actual solutions of Maxwell equations that have been rendered and animated using ANSYS Corporation's FEA frequency solver called HFSS. What we are seeing is an electromagnetic wave traveling from the right to the left along the path of the trace. Again, this is a direct solution of Maxwell's equations. What is shown is the electric field disturbance traveling along the trace. A magnetic field is also present, but its magnitude is so small compared to the electric field that has been ignored in this simulation. The electric field is traveling at the speed of light in that medium. The speed of our simulation has been reduced so that we can actually see the field moving. The field has been projected onto a vertical plane along the center of the trace and onto the ground plane so that we can see how the strength of the field varies. As we move away from the trace, the field strength, indicated by color, changes. The strongest field is indicated in red, and the weaker fields appear in orange, yellow, green, and so on. Notice there is no loss of field strength as the field disturbance moves along the trace. This is indicated by the fact that the colors have not changed. That is, there is no impedance change or friction loss in these systems. This tells us the energy injected into the trace is the same as the energy leaving the trace. Now, charges, currents, and voltage differences do play a role. The electric field disturbance that propagates along the trace has its origin in charged particles. That is, all fields begin and end on charges. And we know these charges in conductors are, in fact, electrons. These electrons are on the surface of the copper trace and the ground plane. The electric field couples between them. This is shown in figure 5b. Now, here's the subtle bit. The charges can and do move, but not at the speed of light. They drift back and forth, knocking into each other as the electric field disturbance passes. They move much like a cork in a pond as the large wave passes. It is the electric field disturbance that travels at the speed of light. The electrons travel at a greatly reduced drift velocity. The bottom line is this: information and power flow in circuits is always and everywhere an electromagnetic field disturbance traveling at the speed of light in whatever dielectric medium is supporting the field. One final point about the microstrip model. Two traces are used in most modern high-speed communication circuits. Digital data is sent along both traces, and the signals are compared and checked for errors. If an error, called a bit error, is discovered, that is, if a 0 is detected and should have been a 1, then the data is resent. This technique is known as Hamming bit error detection and correction. Here we find an example of a common circuit element whose behavior cannot be fully analyzed with only the concepts of currents and voltages. The circuit element is a spiral inductor, and it is found in many applications that require an oscillator. All cell phones, for example, will have several spiral inductors in their circuits. Now, as the animation begins, we see the electromagnetic field disturbance travel along the spiral. In practice, this movement would be at the speed of light. But, again, we slowed the animation so we can get a sense of what's happening. Notice what happens to the color of the field disturbance as it travels around the spiral. It changes in a way that the field strength is reducing. This suggests the field is losing energy as it travels along the trace. No real system is without its frictional losses. Also, notice what happens as the disturbance reaches the end of the spiral. There is an impedance change at the boundary, a barrier. As a result of this barrier, some of the energy is reflected back. These behaviors would be difficult to capture in our simple hydraulic current and voltage model. In this last example, we again return to the microstrip trace on a printed circuit board. However, we have made one slight alteration. We have cut a chunk of the FR4 dielectric and replaced it with air. That is, our dual microstrip traces are passing over a hole. Now, the hole presents an interesting impedance change. And we can see that there is an energy loss by noticing the different field colors between the end of the trace and the beginning. But also notice what's happening at the right side of the trace. Some of the field energy is peeling away from the trace and moving off into space. That is, in fact, the source of electromagnetic interference. That energy will disrupt whatever component it now comes into contact. Now, why does it peel away? Well, the field itself has inertia, and it doesn't easily turn tight corners, such as the bend presented by the air hole in our example. Some of the energy simply rolls away in the direction it was initially headed. The situation is analogous to our experience traveling in our car around a clover leaf at high speeds. We feel as if we're going to be tossed out of our vehicles. Thankfully, our doors and seatbelts keep us safely anchored to our cars.